So this is the January 2014 Regents Chemistry Solutions. So let's get started with the multiple choice. The 1 through 30 is part A, and let's get to it. So first one says, what is the approximate mass of a proton? And we've got these choices here where they say 0.005 U, 1 U, 1 gram, 0.005 grams. Okay, this question, looking at it, will bother some people. Now, you may have been taught that the protons and neutrons are very, very tiny. And you should have been taught that because, well, they are part of an atom. An atom is something we can't see, so the mass of a proton and a neutron is very, very small. So 1 gram, okay, would nowhere near approximate the mass of 1 proton. It's an overestimation. 1 gram of hydrogen atoms, if you know, is a mole of hydrogen, so that would be 6.02 times 1023 number of protons. I guess if you divide that by Avogadro's number, you could get the value. Any case, that being said, 0.005 is still too big. Remember, we're talking about a part of a nucleus of an atom. All right. So in any case, that is still too big, and that's, I think, that's what they were going after, your ability to see the value and understand the smallness of a proton and or a neutron, because they're essentially the same mass in this course. So now we're left with U, and I guess we can only think of this as unit, okay, and this as a unit as well. So the question is, what unit are we talking about? Well, we're probably talking about the atomic mass unit, although not part of the reference table. So what we could do is look at the reference tables and see what kind of clues could help us here. So turning to the periodic table of elements, and the top part gives us a legend or a key of what's going on. Top number is atomic mass, and we should know that this mass number is based upon the protons and neutrons, and of course atomic number is what all atoms are based on, and that is the protons. Okay, also it could equal the electrons because atoms are always neutral. So we talk about atoms as the proton and the electron number. However, looking carefully, the atomic masses of elements are based on carbon 12. So carbon 12 equals 12. And I guess we could say 12 units. And we would say that they're made up of, well, 6 protons and then 6 neutrons. And we consider the electrons to have a insignificant mass. It'll be written as 0 in some places and a -1 charge. So we can look at the number of the relative masses of atoms, and based on the number of protons and neutrons, and come up with this, I believe, unit. We call them atomic mass units, but they're essentially some fictitious units because we can't really measure them. Like we say, they're relative. They're based on each other. All right, so that's where we're going to get the 1 from. Another place we can look to come up with that is table O. Looking at table O, you can see the mass number is up top, and a proton has a mass of 1, and a neutron has a mass of 1, although a beta particle, which is essentially an electron, is given a mass of 0, but don't be fooled, it does have some mass. It's just very tiny, about 2,000 times lighter than these guys. So you can probably come up with the idea of 1 unit is the best guess here for your answer for number 1. All right, so number 1 is going to be 1 U, and that signifies the 1 on top of a proton. And again, atomic mass unit is what we usually use, and I know that U is definitely something that could have messed up with some people, but you could have worked this out. Number 2. An electron in a sodium atom gains enough energy to move from the second shell to the third shell. The sodium atom becomes what? Well, we know the nucleus is positive because of those protons in the nucleus. If you think of the shells as circular, now, of course, they don't go in circular orbits, but we're just going to use these kind of s orbitals, so to speak, to get an idea. So if I've got electrons that move from the second shell with an exact amount of energy to go to the third shell, and of course these are quantized, these are exact amount of energy to go from one shell to the other, clearly you should understand that the closer an electron is to a nucleus, the lower its energy. which we would say is stable. And you would say, well, why is that? Well, it's very easy to understand. An electron is going to be attracted to the electrostatic attraction of the positive nucleus. So electrons are attracted to these things. So in order for them to exist farther away, the electrons have to gain more energy to do so. So the closer an electron is to the nucleus, the lower its energy and the more that the nucleus dominates it. So we say it's stable. And as you probably have already learned, electrons fill energy levels from lowest energy to highest, or from the closer in orbitals to the outer. You've learned that valence electrons are more unstable than the kernel or core electrons. In any case, in order to go from low energy, in this case, to higher energy, energy had to be absorbed. All right, and of course, once you absorb energy, now this electron has extra energy, and we call this the excited state. Electrons get excited when they absorb energy. My son gets excited when he, or can be a little bit hyperactive when he gains energy. Of course, usually in the form of sugar. Okay, so the sodium atom does not become a positive ion. It doesn't lose the electron because that would be pulling the electron away. That'd be ionization energy. The sodium atom can never become negative because sodium atoms only become sodium plus. They're big atoms. They only lose electrons or oxidize. All right, so they become, of course, an atom in the excited state. The ground state is where they start. Okay, case in point, sodium is 2-8-1. And if I was to show an excited state, I would show an electron jumping to the third. An excited state configuration would be 2-7-2. Notice there's what? One less in the third. And one less in the second. And that one is due to because it jumped to the third. But if you notice something, they all equal the same number of electrons. 8 plus 2 is 11 electrons. And if you add these together, also 11 electrons. And why is that important? Because sodium's atomic number 11. Its electrons equal the protons. So obviously, as I overteach every question, choice 3 is the answer. Number 3. Okay, which particle has no charge? There's a reason why they call it a neutron, because it's neutral. But if you need a place to look, table O is your friend. Let's go there. So here's my neutron listed in table O, a very underutilized table. Some people just use it for nuclear chemistry, but I believe it's important in the atomic structure. And you could see that the neutron has a mass of 1, same as the proton. But the bottom number is your charge number. And you can see that a neutron has 0 charge, whereas a proton has a +1 charge. Okay? So number 3 is not 1. Just joking. Number 3 is a neutron. Okay, choice 2. Number 4. Which quantity represents the number of protons in an atom? Okay, well, the number of protons in an atom would be the atomic number. So if we look at carbon 12, that bottom number is the proton number, or the electron number if it's an atom. But the protons in an atom is the atomic number, number 1. Now, going to the periodic table, there are some hints. So going to table O first, you can see that the charge number is +1. Notice a beta particle, which is also an electron, is -1. So protons have this bottom number, neutrons do not. So this bottom number tells you the number of protons, which we call the atomic number. And the reason why we call it the atomic number, because all atoms are identified based on that number. And you could see in the periodic table of elements on top with the little key here, the atomic number is that bottom number, just like you saw in table O, 1/1. And you can see all of these atoms differ because they're differences in the number of protons. The periodic table, the current one, is developed based on the number of protons. Clearly, number 1 is number 4 is 1. I can say it but not write it. Okay, just gotta watch me here. So number 4 is 1. Okay, number 5. The element sulfur is classified as a what? Well, where is it on the periodic table? The choices are a metal, which most atoms in the periodic table are. The metalloids have properties of both metals and nonmetals. A nonmetal, okay, is about a third of the periodic table. A noble gas is a family of nonmetals that is unreactive. So let's go find sulfur on the periodic table. And if you don't know where to find sulfur, or don't know its symbol, on table S, you can figure out that sulfur its symbol is S. Okay, so sulfur is toward the right on the periodic table. Okay, it's right below oxygen. It's in group 16. And you can see this staircase here. That separates the metals from the nonmetals. So these are all your metalloids, which have properties of both metals and nonmetal. Okay, and basically, your metals are to the left, they're larger. Notice the charges they love to become. They love to become positive by losing electrons. Look at your nonmetals. They love to become negative by gaining. Okay, so sulfur is in the land of nonmetals. It's above the staircase and to the right of the staircase. They're the smaller atoms that like to gain and become negative ions. The noble gases is group 18, and these have very stable electron configurations, very low energy, and don't react. So sulfur clearly is a nonmetal. So it's number 5 is choice 3. Okay, sulfur is a nonmetal. Number 6. The elements in group 2. Now, what the heck is a group? A group is a family, okay? And a family is related by similar characteristics or chemistry. They're related because of same valence electrons. I don't even know what the question is. They have similar chemical properties. Families have similar, okay, characteristics because each atom of these have the same number of valence electrons. If they ask about similarity between atoms, do not pick the ones that are going across. Pick the ones that are going down because of the same number of available electrons for bonding. Okay, so that is the answer. Let's take a quick look at the periodic table. So in group 2, we have these elements, and make this a little bigger for our viewing pleasures. Group 2, we have beryllium, magnesium. Notice they have these configurations below the elements. This last number tells you the unfilled shell, called the valence shell. And the other part is called the kernel electrons. These are infilled, and those are stable electrons. The outermost are unstable, and they're involved in bonding. So you can see that group 2, they all have 2 valence electrons. Notice something else. They all become +2. They lose those 2 valence electrons. Okay? So clearly, they're all related by the way that they react chemically, which is they all like to lose 2 electrons to become stable. And they deal with these valence electrons. So same group, same family. Now we have some family names, of course. This is the alkali metals, alkaline earth metals. All right, but same family, same number of valence electrons gives it the similar property. So clearly number 6 is 4, number of valence electrons. 6 is 4. Number 7. Number 7, what is formed when 2 atoms of bromine bond together? So we have bromine, which is a halogen. It's in group 17. And I know it has 7 valence electrons because it's in group 17. And when you have one bromine, and you have another, this one also has 7 valence electrons, they're going to bond covalently. So it's going to make a diatomic element with a single bond. Now, what are they asking for? A monoatomic molecule. Well, a monoatomic molecule would mean, well, one atom, like the noble gases. The noble gases don't bond, so they hang out by themselves, and you can make a case that they're particles, and particles are molecules in some definitions, okay? They're a diatomic molecule, so that's probably the best choice here because they are a particle, although it's interesting that in the Regents they consider a molecule two more different, so they're kind of stretching it here, but the rest of the world considers a molecule to be a particle, whether it's a single atom or atoms bonded to each other. In this case, they're using that definition. Heterogeneous mixture, well, no, this is definitely an element bonded to an element. It's no mixture here. It's a chemical formation, and things are, as substances are made by bonds, not necessarily by, not mixtures. So mixture is out of the case here. There's a bond being made. All right. A homogeneous mixture would be a solution. If it was mixed with water, we could say aqueous and make a case for that. But clearly it's a diatomic. Sometimes your teacher would call it a Hofbrinkel or a Brinkelhof. I use Hofbrinkel, but it's the same thing. These are all elements that love to bond with themselves and are diatomic. All right. So the best answer is choice 2. 7 is 2. Number 8. Gold can be flattened extremely thin into an extremely thin sheet. We know that because of the gold foil experiment. Foil means thin. The malleability of gold is due to, well, again, malleability is the ability to heat metals and basically take them into any shape because of their ability to attract their own atoms very strongly. So malleability is explaining the flattening into a very thin sheet. Also explains why we can take metal and essentially make it into any shape. You can't do that with ceramics or non-metals. They tend to be brittle and break. So they're saying, well, what makes gold or other metals that are malleable able to be shaped or hammered into a thin sheet? Well, it's got nothing to do with the isotopes that are radioactive. Okay, if that was the case, every metal that we shape would be radioactive. So proton to neutron ratios, again, not an answer that we would use here because we're not talking about nuclear chemistry or reactivity. And it's also interesting, guys, to know where you are in the test. Number 8 in the test is probably around atomic structure or bonding or periodic table type of questions. If you go to question number 27 or 28 or 29, those are usually nuclear questions. So knowing where you are in the test could help you steer clear of some things. These are not going to be viable answers here. So moving forward, the reactivity of gold metals. Well, that would not be an answer either because hammering gold into thin sheets is a physical change. And reactivity speaks to chemical reactivity. How well gold reacts has nothing to do with why you can hammer it into thin sheets. That's a physical property. So essentially the best answer left standing is number 3. And you should know that it's because of the metallic bonds that exist between gold atoms. If you quick little review, metallic bonds are nothing more than the positive nuclei of atoms in a crystal. That's right, gold, if a gold bar or a gold ring, it's gold atoms bonded to gold atoms, and these nuclei of gold arrange themselves in a crystal pattern, and it's the electrons that are able to flow between them. We call these electrons a sea of mobile electrons. So these electrons are free to move throughout the entire piece of metal. They're simultaneously attracted. Remember, gold or any kind of atom usually has electrons that are loosely held, generally speaking, although gold is quite an exception because of its reactivity, but not lack of reactivity. But the general idea here is that these electrons are free to move, which means they're able to be moved and conduct electricity and heat. In any case, you're talking about metallic bonds, all right? And metallic bonds, if they were to say, give a chemical formula of something with a metallic bond, you would say Au. And that would scream gold bonded to gold. If I give you something ionic, that'd be like AuCl3, metal, nonmetal. And if I gave you something that was covalent, that'd be nonmetal, nonmetal. So when you're given a symbol just for an element that's a metal, it implies that metal is bonding to itself with this type of sea of mobile electrons arrangement, which gives its ability to be malleable, conduct electricity and heat. Number 8 is definitely 3. Number 9. Let's get some stuff out of the way here. Which term represents the attraction of one atom for another? You've got to get this down. How many times we talked about attraction? Attraction, we have a fancy word for attraction. So when you say this, you got to put the pinky up. And it's called electronegativity. Electronegativity. And of course, that's the answer. There's no place to look. You should know that attraction for electrons or other people's electrons is due to the positive pulling force of a nucleus. So small atoms with small radii are smaller, like the nonmetals, because these nuclei have great nuclear charges that can pull the electrons in closer and thus attract electrons from other atoms. That's why nonmetals tend to gain electrons. Big atoms, their nucleus doesn't have quite the same capability to pull on electrons, so therefore they're easily lost and don't have much of an electronegativity. So 9 is clearly 1. Number 10. Salt water is classified as, well, when you say salt water, I'm thinking about C, and I'm thinking of, let's just say NaCl, if that's the salt we're talking about. Aqueous. I have water, that's the solvent, dissolving the solid. So salt water is salt and water mixed together. It's a mixture. Okay, salt water is not a compound. Even though you say, well, Mr. Grotsky, I see a chemical formula. Yeah, but this chemical formula is mixed with water. Okay, salt and water. Notice salt water doesn't have a different name. When we have oxygen and let's say hydrogen mixed together, it's oxygen and hydrogen. It's until they react, it's just that. When they react and if they react, they become water, something entirely different. Any case, it's a mixture because the proportion can vary. Salt water can be dilute, which means a little bit of salt for a lot of water, or it can be concentrated. These are what makes mixtures unique. You can change their proportions. You can have a salad with a lot of tomatoes. You can have a salad without tomatoes. It's still a mixture. But if something's a compound, if I was to write NaCl solid, that is a fixed proportion of sodium bonded to chlorine. That's a 1-to-1 ratio. Compounds have a 1-to-1 ratio. How much sodium chloride with how much water is not fixed. It's not chemically bonded. So the answer, my friends, if you want to call me a friend, is that the proportion of its components can vary, and that describes a mixture. Number 10 is 4. Number 11. Classic problem. If you've been reviewing these regions, this is one you should not be getting wrong anymore. Which substance cannot be broken down by a chemical change? Chemical change means you're making a new substance by what? Oops, by breaking bonds. A little doohickey there because of the big, okay, my big fingers. So by breaking bonds. So you create a new substance by breaking bonds. Well, ammonia is NH3. That can be broken down into what? Nitrogen and hydrogen atoms. Arsenic is an element. As. Ethane, you should know, is 2 Eths. Eth is 2 carbons. Ane is single bonds. Fill in the rest with the H's. This is a compound. C2H6, it's an alkane. Yes, you can break that down into carbons and hydrogens. Propanol, it's another organic compound. Prop is 3 carbons. The ane part is single bonds. And the al from table R is an aldehyde ending. So this is a compound as well. It's got bonds. You can break them into oxygen, hydrogen, and carbon. So the only choice here that is just an element, which you cannot break down into anything simpler, is the element. So don't be an arsenic. Don't get this wrong. Choice 2 is the answer. How many different ways can they ask this question on every single Regents? Number 12. Number 12, some physical properties of two sample of iodine 127 at two different temperatures are shown in the table. All right, so let's see what we have here. We have selected physical properties of iodine 127. Now, iodine 127 means I have iodine with the mass 127. They're giving me a particular form of iodine called an isotope. All right, and one isotope of iodine, of course, is iodine 127, which you probably have learned helps detect thyroid disorders. It is a radioactive isotope, but that's not what they're after in this problem. These two samples differ in what? Well, one differs in temperature, and the one with the higher temperature is a gas. Its density is very small. At the lower temperature, the same substance has crystals and has a higher density. Okay, so these two different samples are two different phases of matter. One is a dark gray crystals. That screams a solid. And you should know solids are a regular repeating crystal arrangement of atoms, whereas this, of course, says gas. So the first one is a solid, the second one's a gas. The crystal gave it away. Now also the density gives it away. Solids pack much tighter in gases because they're in a crystal structure where gases are flying around the room hundreds of miles an hour. Now they're not different isotopes of iodine. Remember, two different is how you started the question, because they're all iodine 127. All right? They're not mixtures because they're all the same what? Element. And they're not two different substances because they are the same substance. They're the same element. What's a substance? Substance is an element and a compound. Okay, but there's no compound here. So number 12 is 3. Number 13. Powdered iron is magnetic, but powdered sulfur is not. What occurs when they form a mixture in a beaker? If they're forming a mixture, people, they are not chemically bonded. If they're not chemically bonded, the individual properties of iron and sulfur are retained. You have to know that. When things bond, they lose their individual properties. When they're in a mixture, because they're not chemically connected, they retain them. For instance, if you take pure sodium, who has 1 valence electron, and chlorine, who has 7 valence electron, pure sodium is explosive in water. Pure chlorine, of course, is very toxic. It can kill us. When they bond, chlorine takes the electron and becomes negative, but when they bond, okay, ionically, as you should know, what happens is they become sodium chloride, and they have a brand new set of properties. This table salt, of course, the salt on our table, the salt that we put on our French fries is not explosive and is not toxic, okay? We like them on our French fries and when you eat French food, okay? In any case, the point being is that the iron and the sulfur are not bonded. So the iron retains its magnetic properties. And that's the best answer. Iron doesn't lose its properties. Sulfur doesn't gain new properties. They keep their own properties. So 13 is 1. Number 14. Which property is a measure of the average kinetic energy of particles of a sample of matter? Wow, another one. Average kinetic energy is temperature. Temperature is an average of all the particles' motion, okay? And I don't know if you did Boltzmann distribution graphs, but if you got a certain temperature, the average would be somewhere right here. And if an average temperature really represents an average speed. And this would be the number of particles. You have some that are way what? Below, and say some way above. And how do you know that this is true? Well, even on a cold day, a puddle of water still evaporates. That's because there's always some particles that have a higher average, a higher enough energy to escape their intermolecular attractions and go to a gas phase. You don't have to be at the boiling point in order to evaporate. So in any case, you should know temperature is a measure of the average motion. That's something you just have to get down at this point. So number 14 is 4. Okay, number 15. According to the kinetic molecular theory. Now the kinetic molecular theory, KMT as some cool chemistry teachers like to use, is a theory that basically explains how the gases operate or how they respond to different variables. And it's based on a set of postulates that we assume has to be set in order for gases to behave perfectly so that our calculations with gases come out perfect. In any case, I think of kinetic molecular theory, I think of ideal and real gases, and I think of this ideal gas. One way to remember all these postulates is the ideal gas is like the ideal student. The ideal student, okay, is so fixated on the teacher, it has no social skills whatsoever. So when someone asks the ideal student, can I have a pencil? They would say, I like turtles, which is so random. And they move in a random straight line motion. You say, well, why straight line? Because if you asked the ideal student to go get worksheets on the teacher's desk and hand them out to people, he would run to get the worksheets and run back to hand them back out because he wouldn't want to miss anything. So he moves in straight lines. A real gas is not so random, and it would tend to move in bended paths or curved pathways, better English, or correct English, because they want to see their friends. So in any case, straight as an R there. So in any case, looking at these, which one is the ideal student? Gas particles are arranged in a regular pattern. Being regular pattern describes more of a solid. And if they're in a regular pattern, they would not be random. Gas molecules have to have random motion. All right, just like asking an ideal student, what's going, can I borrow your notes or can I have a pencil? He would not answer accordingly because he's too fixated on the teacher. He's not listening to you. You have to be random to be an ideal gas. So number 1 is not the case. The force of attraction between gas molecules is strong. Now the ideal student doesn't attract or is not attracted to the students around him because, again, he's fixated on the teacher. He's only listening and hanging on to every word. So he could have People Magazine's Most Beautiful Person 2014 and 2013 to the left and to the right of him, and he will not be attracted. So ideal gases are not attracted to anything because they're totally independent particles. So this is not. For me, an ideal gas ideally has no attractions. The gas particles are hard spheres in continuous circular motion. All right, hard spheres. That sounds like an old atomic atom type of model. So not liking that either. So that's not a good one. Collisions of gas particles may result in the transfer in the energy. Yeah, that ideal students running to get to the class, so when it bangs into another particle, they both bounce off of each other, and that we say these collisions are elastic. So the best answer here is 4. But when you go through these, the ideal gas or the ideal student, the one that I always remember is very simply is they're random, they go in straight line motions, they're fast because they're lighter and smaller. They tend to have insignificant volume compared to the space they fly in. Hey, the ideal students tend to be smaller people, sorry. And 4, the biggest one is they have no attractions. Real gases really have attractions, are not as random if you think that way. So 4 is the best answer to number 15. All right. And I'll put a 4 here for that sakes. And this continuous circular motion makes no sense. They have to go in a random straight line motion. All right, that's why number 3 doesn't make any sense either. So number 16, moving forward. The concentration of a solution, let's not overpass ourselves here. Okay, the concentration of a solution can be expressed in milliliters per minute. That's a time issue. That looks more like to me a rate, how fast something occurs. Parts per million. Yeah, how much stuff per million parts? That's definitely a solution, okay, which is listed in Table T, right? Table T will tell us that. Grams per Kelvin. That's mass per temperature. That's not going to be an answer either. And joules per gram, energy per gram, like heat of fusion. No, that's energy per how much of the substance undergoing that change. That's not going to work. So the best answer is choice 2, but Table T shows you that too. It's amazing to me how many people do not know and look at Table T to look at all the information they give you, but they give you a concentration what? Formulas. They give you the molarity formula and the part per million. So of course that's concentration right there off Table T if you had no clue. So 16 is 2. Number 17. 2 hydrogen atoms form a hydrogen molecule when? Well, you have to understand that hydrogen is a nonmetal. How do I know that? I know that because it has a pretty high electronegativity, about 2.2. So if this is one hydrogen and this is another, and they both have one valence electron, they're going to be forced to share electrons because their electronegativity, their attraction for electrons or other people's electrons, is pretty high. Nonmetals, as we talked about, have small radii. Why? Because their nucleus, okay, pulls in the electrons. They attract their own electrons so much they pull them in tight, which means they have some ability to yank a little bit on the electrons of other people or other elements. So you need to understand that a nonmetal and a nonmetal are going to be forced to share electrons because they both have these high attractions. They're both small. Whereas a metal, which is a big radius, who has a very little attraction, is going to wind up losing electrons to nonmetals and cause something called ions, and that's an ionic bond. So hydrogen atoms are going to form a covalent bond because they're going to be forced to share. So the two atoms collide, which is important because collisions are the only way bonds are made, and both atoms gain energy. The two atoms collide with sufficient energy to form a bond. So as I'm answering the question, I should read the choices to see before I envelop my explanation here. In any case, so two hydrogens form a hydrogen bond. One atom loses a valence electron to another. This would imply covalent. And because these are both nonmetals, that's not going to happen. One atom shares 4 electrons with the other atom. That's not going to happen because each hydrogen only has 1, although there's going to be some sharing. The two atoms collide and both atoms gain energy. Well, the two atoms are going to collide, that's for sure. Okay, you have to have collisions for reactions, but they're actually going to lose energy. When they form a bond, bonding is a stable state. Both of these hydrogens both feel like, by sharing, to be as stable as helium, a noble gas. So to go from unbonded to bonded, to achieve a low energy configuration, they have to lose energy. Every time you form a bond, energy is lost. So that's why 3 doesn't make any sense. And the two atoms collide with sufficient energy to form a bond. Now, why sufficient energy? Well, remember, you have to have something called an effective collision in order for reactions to go. And effective collision requires 2 things: high enough energy, which is really activation energy, to overcome a couple different energy barriers, and 2, you have to have proper orientation. Okay, those are the 2 things that you learn. So 17 is 4, a little bit going on there in this question, but you should definitely have gotten through it understanding it was a covalent, it was a sharing scenario, and that energy is actually being released to get stable. Stable, bonding, low energy. You've got to get these down. When I say stable, you say low energy. Stable, stable. Thanks for yelling. So they get to low energy by releasing. And you've seen the questions like this. So number 17 is 4. Number 18. All right, number 18. Which type of formula represents the simplest whole number ratio of atoms of elements in a compound? The answer screams empirical. Empirical is the lowest ratio. It's the ratio we find in lab from percentages, not knowing exactly how they're bonded in nature. Case in point as a reminder, C6H12O6 is exactly how this molecule of what? Covalent bonds made up of nonmetals and nonmetals forced to share, okay, exists in nature exactly like this. But if we reduce it to its lowest ratio, all right, we would get the empirical. I'm just giving you an example, and that would be CH2O. And that's an empirical. A condensed formula is just that, a formula that just kind of condenses the structure. I'm not sure exactly how they're getting to that. Structural formula is showing the structure of how these are bonded. This is not a structural formula. Okay, it's a molecular formula. Okay, a condensed formula, as I just learned, is a formula that basically shows the carbon backbone. You may have seen these. I've seen these my whole life, but I never knew it was a condensed formula. For instance, if I was to write propane, propane is C3H8, but it has 3 carbons, so they would write it with this structure. Actually, that would just be, I'm missing here. Let's do that again. So propane would look like this, 1, 2. Each corner of the structure is the carbon backbone, and they would leave out the H's. So that's a condensed formula. I never knew that. All right. Although I've seen those, never knew it was called that. So in any case, the best answer would be, of course, the empirical. I know I overtaught that, but hey, that's what I do. All right, 3. Number 18 is 3. Okay, number 19. The coefficients in a balanced chemical reaction represent. All right, now these coefficients in a balanced reaction help us with something called conservation of mass and charge. So, for instance, if I was to give you hydrogen and oxygen making water, hydrogen means water maker. That's where the hydrogen name came from. Yeah, you're welcome. You got that little important ditty there. But if I balance these, you can see that I have 1 O, so I need 2 O's here. So I put a 2 in front to get 2 O's. Now I have 4 H's, so I put a 2 here. Because of the coefficient of 2, 2 times 2 is 4 H's on this side. Now what do these tell us? Well, they give us ratios. It's a 2-to-1 ratio of individual particles or actual number of moles. So look at the choices here, the mass ratios. Now these numbers are not about mass, although they help us with conservation of mass. They're the ratios of how many particles. There's 2 H2 particles to 1 O2. It doesn't tell me that H2 is twice as heavy. There's 2 of these to 1 of these. So these are ratios of how many. So they're mole ratios. We use moles to help us understand these number ratios in large quantities. So that's why 2 is the best answer. Total number of electrons in the reaction, no. That doesn't make any sense. It's total number of particles. And mole again is helped. Mole is basically a number that we can understand with a certain number of these particles. So 19 is 2. All right, no problems there, I hope. 20. Systems in nature tend to go changes toward what? Well, first of all, energy. Things like to become stable. You should know that stable is low energy, right? Things in nature go from unstable, which is high energy. If you have high energy, you're going to do something, all right? And you're probably going to give it off to become stable. Things that can burn or decay or react tend to do so. Things that are already stable, low energy, don't do anything. Case in point, the noble gases. So things in nature tend to go from high energy to low energy. And if you realize something, that means that most reactions must be exothermic. And that's right, most reactions are exothermic. Endothermic reactions, or reactions that absorb energy, okay, or consume the energy, are far and few between those of exothermic. Now you may say, Mr. Grodsky, I know that endothermic reactions exist. You're right. So if endothermic reactions exist, it can't just be high to low energy. There must be another factor. And that factor, of course, is entropy, which is the chaos theory. things in nature go from order to disorder. That's how the universe works. Okay? The amount of entropy is always increasing in the universe. We try to fight it. Okay? And you think about your room at home, or your room at college, or your room anywhere, it does not get clean by itself. It naturally becomes disorganized without you trying. But to fight the universe, you have to what? Put energy into the system to change it. So when your folks tell you to clean your room, tell them, Mom, Dad, I can't fight the way of the universe. Probably not going to work. So we go from high energy to low energy. So changes toward lower energy and higher disorder. Remember, entropy is a measure of disorder. So things tend to go toward the lower energy exothermically, and tend to go toward higher chaos. Absolutely. So 20 is 1. Number 21. So 21, which form represents an organic compound? You have to have carbons to be an organic compound. Okay, there's just no ifs or buts about it. So that's number 2. If you didn't know that, table P, Q, and R show us. Table P is organic prefixes, which is based on a number of carbons. We have table Q, homologous series of hydrocarbons. How many carbons and how they're bonded leads to the naming system. And then we have the functional groups, which all have what? A carbon backbone. Okay? Number 22, which class of organic compounds contains nitrogen? If you don't have a clue, okay, class of organic compounds tends to talk about the functional groups. And we were just there at number 21. So I need a functional group. It's I there. And a functional group is nothing more than an arrangement of atoms on a carbon chain. And because of their arrangement, it gives them a distinct type of property. It gives the carbon chain a distinct property because of this arrangement of atoms. So let's go to table I, look up aldehydes, alcohol, amines, and ethers. So here we are, table R, and alcohols don't have any nitrogen. Ether there's no nitrogen. Look at the example. Aldehydes, there is no nitrogen. There's no N here. We go down to the amines. Oh, there it is. And there's an N there. So clearly amine is the answer. Just have to know where to look. So amine's the answer. So number 3 is 22. 23. Which term identifies a type of organic reaction? All right, well, this is going to have to come from memory. Deposition is a gas going to a solid. It's a phase change. Okay, it's kind of like how snow exists. Not kind of, it's how snow is made. Water droplets, or water vapor, I should say, in the gas phase becomes a solid. Distillation is the process where we take a mixture, usually of liquids, and we separate that mixture based on the individual properties of the liquids that are still retained because it is a liquid, and you boil off at different temperatures the different components of a different liquid. Okay? Sublimation is the opposite of deposition. It's a phase change where a solid goes directly to a gas, like dry ice. CO2 solid becomes CO2 liquid. So the only thing left is number 3 that makes any sense. So if you forgot, they kind of gave you choices to help remember that. So number 23 is 3, and of course esterification is what we make esters from. And that of course is from an organic acid that has this Cu group, and it reacts with an alcohol, an OH group. And if you remember, the water comes out to dehydration synthesis. And what you're left with, go back to blue, is the C. That's the C here. The C double bonded to an O. And now you have the O and the CH3. And that's your ester. Okay? And of course, esters are sweet-smelling compounds. They're aromatic. Any case, little piece of information. 24, which compound class is a hydrocarbon? Just hydrogen, just carbon. Okay, well, butanol is an alcohol group, has an OH. Butanone from table R has a carbon double bonded to an O from table R. And butanal is an aldehyde with a C double bonded to an OH ending. So my friends, in chemistry, we have compounds other than carbons in these. So aldehydes, al, olwels, ols, and butanone have these. Let's take a look at table R to see that. All right, so we have the aldehydes, and they've got this carbon double bonded to an O, so it cannot be a hydrocarbon. We have the alcohols, have the O as well. And we've got the ketone, which has the what? Carbon double bond to the O. So we can't have O's if we're hydrocarbons. So they mention butane. Well, from table, whoa, I'm doing a little dancing here. Table Q, butane. But just tells me that there are, or but is 4 carbons. And the ine tells me that there is a triple bond somewhere. So if I make it on the first one, fill in the rest with H's, and that's butane, just carbons and H's, hydro. So butane, 24 is 2, because that's the hydrocarbon, just hydrogen, carbon. The rest have the oxygens on the functional groups. 25. If an oxidation reduction reaction, I kind of like the word redox, the number of electrons lost has to equal the number of electrons gained. This is where we get conservation of charge. You can't create or destroy an electron, so the same number are passed around. And you know this because when you balance a redox reaction, if you had a good teacher who showed you how to do this, for instance, let's get rid of this for a second, you might have seen the following. Let's say I had zinc oxidizing. Zinc goes to zinc plus 2 electrons. And let's say we had silver plus ions getting reduced. Silver plus, so the silver plus ion gains an electron. Becomes silver 0. Now I probably should have wrote the chemical reaction. The reaction, overall reaction, let's make it a net ion. Zinc 0 plus silver plus goes to zinc plus 2 plus silver 0. And your teacher said, okay, write your half reactions. This is, of course, the oxidation. We're losing electrons, and this is the gaining. And, of course, your teacher said, well, you have to balance the electrons. Zinc is giving off 2 and silver plus is gaining 1. So you probably learn, throw a 2 down here and you distribute that 2. 2 times 1 is 2, 2 electrons, 2 this. And the magic here is that the 2 electrons cancel. Once you balance the electrons, you automatically balance your reaction. So equal to the number of electrons gained and lost. So obviously, party people, 25 is 1. Number 26. Number 26. Which substance is an electrolyte? Well, my friends in chemistry, an electrolyte describes compounds that when in water dissociate into free ions. And there are 3 things that dissociate into free ions. So you're looking for something that breaks apart into free ions. Very important. So the first one are salts. Fancy name for ionic compounds. So if you had sodium chloride, that dissociates into Na plus and Cl negative. These are free ions which can move in a solution to conduct charge. The second things are acids. You should know that acids dissociate, like HCl, into the proton and the conjugate base, the negative ion. These are free ions. And then the last thing are bases. Bases will ionize water or dissociate into hydroxides, like NaOH is a base listed in table L, I believe, and that's Na plus NOH minus. So I'm looking for something that's either an acid, base, or a salt. I see I picked the right choice. This is a molecular compound that's covalent. Oops. Christmas. So hold on. And so this one conducts. So this one is a molecular compound, does not conduct. It's made of nonmetals bonded to nonmetals. This one looks like it's a base, but it's an alcohol according to table R. So that one does not conduct. And of course, this is also molecular. The word molecular means they make molecules, which means they are not salts. They are covalently bonded, and they're not acids or bases. So the only answer here that fits under these free ions is NaOH, which really is a salt that's special because it gives a hydroxide away. So this is your answer. 26 is 3. And of course, don't fall in love with the idea that this has to be a base. The Regents loves to give you alcohols. From table R, they say R with an OH is an alcohol. Okay, don't think everything with an OH is a base. Okay, this is a salt, a positive ion attracted to a hydroxide. So don't fall for that. 26 is 3. Or should I say number 27? Which energy conversion must occur in an operating electrolytic cell? Electrolytic cell is electricity is needed. So this is the one that needs a battery. Why? Because it's non-spontaneous. It's like electroplating, electrolysis of a fused salt. You need a battery to make a reaction that doesn't normally occur. So we take electrical energy from the battery. To make nuclear energy? No, that'd be interesting. To make a chemical reaction, which is chemical energy. So you had to realize that this is not the battery. The battery is called a voltaic because of Alessandro Volta and his first battery. And a battery would take chemicals to make electrical. So the battery would be number 3. Of course, 4 and 1 is silly. Okay. Number 27 is choice 3. I'm sorry, choice 1. Sorry, I'm looking at my examples that are not. So number 27 is 1. Okay, where electricity is used. Sorry. Number 28. Which compound yields H pluses? Who gives off H pluses? All right, you gotta know who's giving off H pluses. H pluses are acids. Acids give off H pluses, and if you don't know that, a table comes to the rescue. So here is table K, and it gives common acids, and look what's in front, H's. Why they put the H's in front? To help remind you that these things come off. They all come off to give off H pluses. Or they produce H3O pluses if a water holds on to them, called a hydronium ion. They make the pH low. So you're looking for an acid. Notice the acid given to you also is also written as a structural formula because this is an organic acid. This is ethanoic acid or vinegar. So the Cu group is an acid as well. So the answer is an acid, which is listed right in the table we just looked. This is an alcohol, table R. This is a base, okay, and this is another base on the table L below it. So number 28 is choice 4. Number 29. Which statement describes the relative masses of 2 different particles? Okay, so we want the relative masses. A neutron has a less mass than a positron. A beta particle has less mass than a neutron, an alpha particle. So we're comparing these particles based upon their relative masses, which just means their masses above the number. For instance, in table O, you'll see a neutron has a mass of 1 relative to the other chemicals or particles and a charge of 0. A beta particle is given this symbol of an E, 0 mass and 0 relative mass, and a -1 charge. Alpha particle on table O is given as a helium nucleus, atomic mass of 4 and a +2 in the nucleus. All right, and a positron given in table O is nothing more than a 0, E, and a +1. I'm getting all of these in table O. And I'm just looking at the top number. So this is a alpha particle is here, a positron is here, a beta particle, sometimes called an electron, is here, and of course a neutron. So what's the best answer? Go through the choices. A neutron has less mass than a positron. Well, a positron has less mass. It's got a 0, so no. Beta particle has less mass than a neutron. Well, yes, it does. Beta particle is given a relative mass of 0, and a neutron has a mass of 1. As you've learned today's test, 1 unit. Okay, 29 is 2. Number 30. Okay, again, know where you are in the test. Number 30 is the last unit on the test. The test basically goes in order from atomic structure, periodic table, bonding, through all the other units you've learned up until redox, organic, and now nuclear. So it always seem to end on the last 2 or 3 questions up until 30 is nuclear. This question on table O was a nuclear question. Okay, 28 was an acid-base question. So these are the last units you learn. So the test goes in order. So you're in a nuclear area. What words did you learn? Well, condensation is a phase change. It's a physical change. We're not talking about physical changes of intermolecular attractions, but you should know condensation is a gas goes to a liquid. Vaporization is a liquid going to a gas. Single replacement is a type of redox reaction like copper and aluminum chloride. Go to what? Copper chloride and aluminum. Although that's non-spontaneous, you can see that with electricity I could force that to happen. All right, but it doesn't matter. These are all involved with these are attractive forces. These deal with electrons being passed around. We're talking about nucleus changing. Natural transmutation is about a nucleus changing. These have nothing to do with the nucleus. So 1, 2, and 3 make no sense. And I love to ask these types of questions. These are chemical or physical changes. And number 4 is about a nucleus changing. Case in point, natural is like carbon-14. Undergoes natural transmutation naturally by itself, nothing else in the reactant side, gives off a beta particle. And what else? Well, what number plus a -1 equals 6? That'd be 7. What number plus 0 is 14? 14. Who's atomic number 7? Look at the periodic table, it's N. So number 30 is 4. Okay, number 31. Which ion has the smallest radius? Now we're in part B1, which these types of questions tend to be a little more challenging. Usually have a second part to them or 2 steps to them. Sometimes I see that, sometimes I don't. But in this question, I want the smallest radius. And notice they're giving me the ions, okay, of these. So what we need to consider is where these guys are in the periodic table. Oxygen, sulfur, selenium, and tellurium. Let's go to the periodic table. And here they are, oxygen, sulfur, selenium, and tellurium. Okay, let's zoom in, a little up close and personal look at them. And you can see that they're all in the same group. They clearly all have the same number of valence electrons. They all become -2. They all want to gain 2 electrons to become like their noble gas counterparts here. Let's make sure we can see that. Okay. Now, what am I talking about here? Well, they want to know who's the smallest. Well, we know, or we should know, that going up the periodic table, atoms get what? Atoms get smaller. The electronegativity increases. So the oxygen is already the smallest atom. As you go up, you get smaller. The smallest atoms are the nonmetals. As you go down, you get bigger. The biggest atoms, guess what, are your metals. Polonium's a metal, whereas oxygen is a nonmetal. Sulfur is a nonmetal. Okay, this is probably a metal, more like a metalloid if anything else. Selenium is a nonmetal. Any case, the point being is these all gain 2 electrons. Now, when you gain electrons, the radius gets bigger. Okay, so they're all going to get bigger similarly, but oxygen already starts out the smallest. So as they all get bigger, the one that will stay the smallest is the one that starts out the smallest, if you want to think that way. So oxygen is going to be the answer here. Now, you can also say, well, oxygen is going to fill its second energy level, whereas sulfur is going to fill or almost fill its third, and so forth as we go down here. So this has the least, oxygen has the least number of energy levels that are filled when it gains 2 electrons. Therefore, it would be smaller because it has less shells. Anyway, I like to think about that, but oxygen is your answer. So O-2 has the least number of filled shells, or it starts out the smallest and now they all get bigger the same amount because they're all gaining electrons, and electrons outnumbering the protons, or if you gain weight you get bigger. When you become negatively charged, your radius gets larger. Any case, O-2 is 1. 31 is 1. 32. Number 32 states equal amounts of ethanol and water are mixed. Mixed. Okay, not bonded. At room temperature. Okay, and 101.3 kilopascals. That's standard pressure. Which process is used to separate ethanol from the mixture? So we've got a mixture of liquids, and we don't separate liquids by filtering them. Ionization is making them into positive or negative ions. Reduction is making them gain electrons. Distillation is the process by which we boil off the liquid who's got a particular boiling point due to its individual properties that are retained in the mixture. So distillation is how we separate liquids based on their individual boiling points. 32 is 1. All right, distillation. Number 33. A sample of a substance has these characteristics. Melting points of 984, hard, brittle, poor conductor. That jumps out at me. Poor conductor of heat and electricity as a solid. That really jumps. Good conduct electricity as a liquid or an aqueous solution. See, for me, all of this is a winner for me. I look at that and I know exactly what I'm looking at. I'm looking at an ionic compound. Ionic compounds are positive and negative ions. That in a crystal, these ions are not free to move. Therefore, they tend to have poor conductivity of electricity and heat because these ions are in fixed positions. Their melting points are pretty high because positives and negatives are a pretty strong attractive force, and in a crystal lattice where you're surrounded by other negatives or other positives, it makes it have a lot of stability. The brittle side might get you, but things that are rocks can be brittle because they can be cleaved at these points. But the best thing is they love for you to know that ionic solids, yes, a good conductor if what? Liquefied in a molten state when they what? The ions are free. If you free these ions from the crystal, they're called an electrolyte. Okay, they can conduct as a liquid or an aqueous when the ions are free, but when they're not free, when they're locked in their crystal structure, they're terrible conductors. A molecular compound is something covalently bonded, like ice or water. That's going to have a low melting point. It may be brittle, and it's never going to be a good conductor in an aqueous solution. Radioactive elements, that just doesn't make any sense. Metallic element is something we've talked about in this test. It has metallic bonding, like, let's say, copper. Copper bonded to itself. But copper is going to be a great conductor as a solid because of the free-moving electrons in its crystal structure. It has a sea of mobile electrons. In any case, 33 is 4. 34. Given the balanced equation representing this reaction, which statement describes the reaction? Well, gosh darn it, I see that energy is needed. All right, so clearly I'm going with endothermic. Anytime energy is on the reactant side goes before the product side. It's on this side of the arrow. These have to react to form products, so you need the energy with the N2 to make this happening. And of course, bonds are broken because you're taking something N2 and making it into single atoms. Okay? Now, they love to give you this question without the energy, and you should know if I was to white this out, this is still endothermic. Not because it's not written there, it's because anytime you want to break bonds, break bonds or breaking something requires energy. Bonding is a stable state. Being a free atom or a single person, you have more energy. Think about the single people at a party. They dance crazy. They want to show their feathers. They're like peacocks. They want to show their feathers, and they want to show how good looking they are or something like that. And they're dancing like crazy to get noticed, whereas the couples are usually boring people sitting down. So the bottom line is when things are bonded, they're stable. They have what? That stable what? Electron configurations, noble gas. And when you break them, you need energy. Okay? To make, you're going to go from a low energy state to a higher state, you need energy. Okay, 35. Let's go see. When lithium reacts with bromine, now lithium is a metal. It's Li. It's to the left of the staircase, and bromide is above the staircase, non-metal. They form a compound. Each lithium ion, okay, well, it's a metal. And you should know at this point, metals lose electrons. They oxidize. This is a nonmetal. Nonmetals are smaller. They gain electrons. Metals are bigger. The electrons tend to be farther away from the nucleus, easily lost. These guys have what? Low electronegativity, which is attraction for electrons. Bromide has high attraction or high electronegativity. So metals lose electrons, but if you didn't know what they did, go to the periodic table. So here's our lithium, and lithium, look at the charge it likes to become. It likes to become +1. It's a metal. Look at all the metals, guys. They all become plus. If you're below the what? Staircase. Here's my staircase. You are a metal. Everything to the left and below the staircase is a metal. They lose electrons. Look at the bromide. It becomes negatively charged if the other one's positive. They gain electrons because they're smaller. Okay, so lithium becomes +1 as metals lose. So each lithium becomes positively charged. And you become positive by losing negatives. Electrons are negatively charged. Okay, metals lose electrons. Remember Leo the lion says, Grr, they get oxidized, losing electrons. And they do so because they hold on to them loosely. That's what makes them metals. So 35 is 3. Number 36. A beaker with water and the surrounding air are all at 24. So sometimes it's nice to draw. Got a beaker with water. It's at 24 degrees Celsius. The air surrounding it's at 24. Thermal equilibrium. Okay. After ice cubes are placed, so let's place some ice cubes in the water. Heat is transferred from what? Well, ice at standard pressure is going to be about 0 degrees Celsius. Okay, they're both at that temperature. Oh, oops, I just lost my beaker. Happens to me sometimes. Okay, now, things in nature travel from cold to hot or hot to cold. Do not think the cold from the cube flows to the water. That doesn't work that way. The reason why ice cubes feel cold, the reason why ice cubes make your drink cold is because heating, or in this case, when a solid goes to a liquid, that's an endothermic phase change. You need energy from the environment. So heat flows from hot to cold. So heat is transferred from the ice cubes to the air. No, air is warmer. The beaker to the air. Beaker to the air have the same temperature. Water to the ice cubes, the water to the beaker. No, I would say the best choice is the water to the ice cubes. The warmer water travels to the colder, and basically the ice takes the energy from the water and makes the phase change occur, which makes the water go down in temperature. 36 is 3. Okay, 37. A sample of chlorine gas is at 300 Kelvin and at 1.0 atmosphere. At which temperature and pressure would the sample behave more like an ideal gas? Okay, an ideal gas is like an ideal student. An ideal student is so fixated on the teacher teaching that they have no attractions. No attractions with their other students, right? They could have People Magazine's most beautiful person to the left and to the right of them, and they would not be attracted because they're so focused on a teacher. So, if we want to go from they want to go from which to which here? Which temperature would a pressure would behave more like an ideal? So, if we want to go to an ideal gas, we're going to go from a condition that's probably real. Since most gases are real, there's no such thing as an ideal gas, just like there's no such thing as an ideal student. So I take a real gas that really has attractions, which means the gas particles are closer together. Hey, how you doing? And they go to a scenario where they have no attractions, they're farther apart. The only way to do that would be to, number one, speed them up. So I would say higher temperature. All right. Right? Because I want them to go faster so they have less chance to attract, right? And I want to decrease the pressure, right? The pressure that's currently on them is pushing them too close. So if I decrease the pressure, all right, on them, there's less of a force on them, they would move farther away and have what? No attractions or less attractions. So I'm looking for the highest temperature, lowest pressure, and that's why choice 4 is the answer. For me, the way to remember this is a real gas really has attractions, and an ideal gas ideally does not. So 37 is 4. Number 38. When a sample of a gas is heated in a sealed rigid container from 200 Kelvin to 400, the pressure exerted by the gas is? All right. So what's happening to my temperature? It is doubling. They said a sealed rigid container. That screams to me that the volume that the gas is occupying is constant. It's fixed. It's not going to change. Let's look at our equation, which is from table T. Pressure times volume over temperature equals pressure times volume over temperature. But since volume is held constant, we have pressure over temperature equals pressure over temperature. So how is pressure and temperature related? Well, my friends in chemistry, pressure and temperature is directly proportionate. Now, if you don't know this, it's easy to understand. Pressure is the force due to molecules colliding. Okay, well, temperature is what? Is their motion. So if you double their speed or their motion, wouldn't you double their pressure, their collisions? Yes. So this is a direct proportion between pressure and temperature, sometimes called the Gay-Lussac's law. Okay, so 200 to 400, so the pressure would also double. And doubling would be increased by a factor of 2. All right? That's what a factor of 2 means. A factor of 2 means doubling. A factor of 3 is tripling. A factor of 4 is quadrupling. So this is directly proportionate. It's pretty intuitive. Temperature doubles. The speed at which molecules are moving doubles. Well, guess what? The number of collisions would double if the volume is constant. Obviously, if the volume can expand, then it wouldn't change. And obviously, the number of particles in the container are also the same. So this is a pretty intuitive question, but you can also solve for it by putting some numbers in, right? Let's make the pressure 1 atmosphere. And let's make the temperature 200. Let's solve for the pressure when this is 400. So I made up a pressure, but who cares? We're going to see if it doubles. So this is Kelvin. So we solve for this by, if you remember algebra, this goes to the top. So 400 Kelvin times 1 atmosphere. Oops, little doohickey. Let's get rid of that. 1 ATM all over 200 Kelvin. You can see that our units cancel. 400 times 1, imagine that is 400 divided by 2. 200, it gives me 2 atmospheres. And notice all of your units cancel. Kelvins cancel except atmospheres, so I'm left with 2 atmospheres. So I solved for it if I wanted to. Now I had to make up a pressure unit, but 2 ATM. Nice little problem. So 38 is number 2. And I know the wording can get people sometime. A factor of 2. You know, a factor of 2 is just doubling. Okay, so 28 is 2. 38 is 2. Number 39. If you've been doing many of these Regents tests, you've seen many of these. And what we're doing here with bright line spectra of the elements is basically we're sending them into, basically we probably have tubes of gases that we're putting electricity through. We're exciting these electrons. They're going farther away from the nucleus, right? And when they get excited from this positive nucleus, they jump away and they get excited in their excited states. And then when they jump back to their ground state and stable, they have to give up that extra energy, and they give in the form of electromagnetic radiation or light in specific wavelengths. Okay? And if you've looked at these in your class, you notice this is called spectrum analysis. Okay? And you can break down the light given off into individual wavelengths of light. Pretty cool stuff. But we can identify elements based on these wavelengths of light given off. Now, the reason why different elements give off specific wavelengths because every atom has exact quantized leaps from their ground state to their excited state. So the individual leaps or the individual jumps are represented by these wavelengths of light. In any case, the point being is that if I've got a mixture of elements, I should have a mixture of the lines given off by these electrons jumping back. So it's pretty simple stuff. So given the bright line spectrum, okay, here is the data formed from 2 elements. Well, I got one around here. So it looks like this line is, no, I'm sorry. So I got one less than 650. Okay, so it's this line, I'm sorry. So let me just match these up. Usually they're underneath each other, so this is a little different type of problem. You have to use your measuring skills a little bit better. So we've got this line here with respect to the 650. And then we have this line comes from here, and these 2 other lines come from element A definitely. These 2 little lines have to come from element D. So you add these lines together, so it's A and D. All right, choice 1. So 39 is choice 1. Number 40. In the graph below represents the relationship between time and temperature as heat is added at a constant rate to a sample of a substance. During interval AB, which energy change occurs for the particles in this sample? Okay, well, you should know that this is the solid phase, the liquid phase, and the gas phase. Tremendous energy. This is a solid going to a liquid. The phase change, the temperature stays constant. And this is a liquid going to a gas. Okay, so during interval AB, which is right here, we know that the kinetic energy, which is the same thing as temperature, the average, I should say, the average kinetic energy is staying constant. Okay, so the average kinetic energy increases? No. Average kinetic energy decreases? No. It stays constant because the kinetic energy, or the thermal energy, is being converted to potential energy at the phase changes. So the kinetic stays constant, but the potential increases. So as we add energy to a system, the potential always increases, and especially at the phase change, because when you have a solid who is in a fixed position, has less potential for movement than a liquid who can move independently out of a crystal lattice. So liquids have greater potential for movement than solids, so they have greater potential energy. So as a solid becomes a liquid, the potential energy increases. Even though the line is staying constant, a thermometer measures temperature, which is kinetic energy. A thermometer does not measure potential. Okay? So 40 is definitely going to be 1 there. The potential energy increases because the energy being absorbed is converting a solid into a liquid, and liquids have greater potential than a solid. So 41. All right, given the potential energy diagram for a reversible chemical reaction. Each interval on the graph labeled potential energy, let's make this smaller, represents 10 kilojoules of energy. What's the activation energy of the forward reaction? Okay, well, the first thing I do with these things is see where I start and see where I finish. I notice that I'm going up a box. So this is an endothermic curve. It's a potential energy diagram. And the delta H is positive. Do you need to know this for the question? No, it's positive 10 actually, joules. Okay, because I'm going up. In any case, the activation energy for these reactants to become these products, they have to overcome this energy barrier, which is right here. So the activation energy is the energy needed to overcome this barrier. Sometimes, hey, if you want to ride a slide, don't you have to climb the slide to get to the top? Yes. So here's 10, 20, 30, 40. So it's about 40 kilojoules. In order for you to ride the slide or the chemical reaction to go, you've got to climb the slide. It's the energy you have to put in to ride the slide, the energy to put in to overcome the energy barrier or the activation energy. So number 40, is this 41? Is 3. Okay, 42. I can speak, which condensed structure, let me go with the condensed structural formula, represents an unsaturated compound. All right, a structural formula represents an unsaturated compound. Now, if it's unsaturated, that means it's not holding, or it's not saturated, it's not holding the max amount of H's. So I'm looking for something with a double bond or a triple bond. Now, if I look at CH4, I can do this a couple different ways. I can draw these out to see if they need double bonds. If they got double or triple bonds, party people, now I know that instead of having a lot of H's, I'm going to have a lot less H's because I'm using some of the bonds that could be used for hydrogens for a bond between the carbon. Case in point, number 4. Oops. Number 4, or I should say the fourth choice, is methane. I have a carbon and I have these H's here. Because I'm not bonding to any other carbon, I am maximizing the amount of H's I have. So number 4 is clearly saturated. By the way, it's an alkane. It's called methane. Number 2, let's draw the structural formula. I have CH3, so C with 3 H's. Every carbon must have 4 bonds because it has 4 valence electrons. This carbon has 2 H's, and this is CH3. Look at that. Every carbon has a single bond, and I have this maximum amount of H's. Propane. So this is also saturated. It has single bonds. It's a saturated hydrocarbon called propane. 3 carbons is a prop, and ane because of single bonds. Look at choice 3. CH3, having 1 bond between the carbons, CH3, so C2H6, also, the way this is drawn structurally for me is telling me that this also has 1 bond. Let's do number 1, which has to be the answer now. CH3, I have a CH, CH, CH3. Now you can see something here. This CH and this CH, why aren't they CH2s? If you look, this carbon has 4, 1, 2, 3, 4, a bond with the carbon, but 3 bonds with H's. This only has 3 if I have single bonds. The only way to explain it to CH is I need a second bond here so that carbon has 1, 2, 3, 4 bonds. So this is telling me I have less H's. Now another way to do this is you go to table Q. Okay, table Q, very important. The alkanes are saturated, have the maximum amount of H's. This is C2H6. This is C2H4 if it's got a what? A double bond. This is C2H2. Notice I have 6 there. C2H4, sorry. So let's do this again. So if it's got single bonds, it's C2H4. 6 that's got a double bond, C2H4. It's got triple bonds, C2H2. Notice I'm losing 2 electrons every time I gain an extra bond between the carbons. So you need to know that this is your saturated hydrocarbons, and these are your unsaturated. It's important you know that. Now, if I'm looking for something unsaturated, I'm looking for something that does not fit the CnH2n plus 2 general formula. So this formula will tell me if it's saturated or not. Let's go use it. So from our table Q, CnH2n plus 2 is the general formula. So if we go to table 1, choice 4, I can do this. All right. I have 1 carbon, and then that goes 2 times 1 plus 2 is H4. That works. That is saturated. That's why that's not the answer. Look at this one. I am C3. Now double it. 6 add 2, 8. It should be H8. The max amount of H is 1, 2, 3, 4, 5, 6, 7, 8. So this again fits the formula, so that means it's saturated. Look at this one. C2. Double it, that's 4, plus 2 is 6, H6. As you can see, I have 1, 2, 3, 4, 5, 6. So this is saturated. But this one is C4. If you double it, it becomes 8. Add 2 should be 8, should be H10. If you can't, number 43, which element reacts spontaneously with 1.0 molar HCl at room temperature? Okay, well, first and foremost, spontaneously means that the reaction occurs with a direction, which means that it occurs. It's going forward. So when we ask about spontaneity, normally when it comes to a redox reaction like this would be, okay, we'd use net potentials, but we're only left with table J. So what's happening here is we have hydrochloric acid, okay, plus one of these metals. So let's pick zinc. And what's going to happen is, if it is spontaneous, zinc is going to give electrons to something. Okay, zinc is a metal. Metals can only oxidize when they're in their standalone zero elemental state. As you probably remember, metals tend to be bigger. Their electrons are farther away from the positive nucleus than nonmetals, so they're easily lost. Metals only become positive ions by losing electrons, and losing electrons is oxidation. If you remember this mnemonic, Leo the lion says grr. So losing electrons is oxidations. Metals can only lose because they only become positive ions. If you look at your reference table, you should know that these are your metalloids, and of course these are your nonmetals above the staircase, including H. All the rest are metals, and if you look carefully, as I'll zoom in, all right, if you look carefully, metals become positively charged. All these metals all become positive. Why? Because they lose electrons. Nonmetals like carbon and everything else to that side, okay, does not lose electrons. So all these guys are metals. The nonmetals off to the right, they tend to what? Gain electrons and become negatively charged. So metals like zinc, as you can see, or copper, or gold, or silver, all become positive ions by losing electrons. So clearly these are all metals, they all lose electrons, they all oxidize. Okay? Now, what's happening with the acid is that the acid, HCl, is going to become H+, dissociate into its proton and its conjugate base. It's the H+ that is able to accept these electrons. So electrons are going to flow from the metal to the H+. And essentially H+ is going to gain electrons and become elemental hydrogen. And if each one of these gains an electron, and you have 2 hydrogens, you're going to make the diatomic hydrogen. So H2, we're going to make H2 gas, and you should know that hydrochloric acid plus a metal, if it's spontaneous, will make the hydrogen gas. Now, of course, the zinc, when it loses 2 electrons, is going to become zinc plus 2. And, of course, the chloride ion is left. And, of course, to make the final, you crisscross these, so you have 2 chlorines to 1 zinc. And that's how we would make that compound. All right, so in any case, the question is, who is spontaneous? Who is going to oxidize enough, I should say, to drive the H plus to get reduced? H plus is gaining the electrons, and we can write these half reactions if you need to see them, and it's good practice to be able to do this. So what we're saying by this entire process is the H plus, let's make that smaller, the H plus, or 2 of them, are going to gain 2 electrons from the zinc, and they're going to become hydrogen gas. And the zinc 0 is going to lose 2 electrons to become zinc plus 2, as only metals can do. So, if in fact this is spontaneous, in table J, if this is going to work, the metal that oxidizes better be above the one who reduces. So copper, gold, silver, and zinc, let's go to table J. So table J, here we are, and the metals we had involved, okay, were copper, silver, gold, zinc, and we're making H2 gas, which really means that 2 H pluses, we're gaining 2 electrons, which means this one right here, or this half reaction, which is implied by H2, is getting reduced. So therefore, I need something above it to oxidize. And that's how this table works, because it's a list of metals. The most active metals are the ones that lose electrons the best or oxidize the best. So if this is going to be spontaneous, if this is going to work, we have to have a metal that's strong enough of pushing its electrons onto the H plus. And a way to do that is saying that the one who oxidizes has to be above the one who reduces on this side of the table. As you can see, zinc is above H2, where the 3 other metals are below. So that's why zinc is the answer. So choice 4 is the one that's spontaneous, which means it'll work, it'll have a directionality. Number 44. Okay, number 44, they give us this balanced redox reaction. I know it's a redox reaction because I can find myself a couple of zeros, which means if I see elements that are in the elemental state, they're 0, and if I find one of them in a reaction, I know they're going from a 0 into another number, which means the oxidation numbers are changing, electrons are being passed around. Here's the question. What is the number of moles of electrons gained by 3 moles of lead ions? Okay, well, let's look at the half reaction specifically. Let's pull this out. Pb plus 2 is going to go to Pb 0. And if you notice, from a plus 2 to 0, I've got to put 2 electrons involved, and I put the 2 electrons on the side that make both sides of each half reaction have the same charge. That's your check. So -2 and a plus 2 is 0 on this side is 0. If I was to put the electrons on this side, it'd make it -2 on this side. So Pb plus 2 is getting reduced. Its charge is going down because it's gaining electrons. Leo the lion says grr. But the question states, how many moles of electrons are gained? Now we know they're gaining because, well, it's on the reactant side by 3 moles of lead ions. So wait a minute, I know that one of these produces 2 electrons to make this work. If I put a 3 here, that means I would have to put a 3 here, because conservation of mass, but 3 times 2 is plus 6. How many electrons would I need now to make this 0 on both sides? And you're right, I would have to put 3 times 2 is 6 electrons. So what I'm doing is multiplying everything by 3. Right? For every 1 lead, there's 2 electrons, or 1 lead plus 2, there's 2 electrons. So for 3 of them, there's 3 times 2, 6 electrons needed. And that's why the answer, okay, is 6 moles. Now 6 moles of what? Electrons. What's the number of moles of electrons? In one of these, we needed 2 electrons, but in 3 of them, 3 times 2 is 6 moles of electrons. So therefore, number 4, or number 44, is 4. All right. Number 45. What is the total amount of heat released when 5 grams of water is cooled from 20 degrees Celsius to 10 degrees Celsius? All right. Well, this is an energy question, and we have 3 formulas to look at. So let's go there. Table T. So I'm at the bottom of Table T, and I see that the heat reactions, there's 3 of them. Q equals MC change in T, Q equals MHF, and Q equals MHV. So I have 3 equations where I can solve for Q. Now heat, of course, is joules. The question is, which formula do I use? Well, one way for me to make this simple is to understand where you are in a heating or cooling curve. This is how I help my kids remember what formulas to use here. So if you can visualize a heating and cooling curve, let's just make it a heating curve. Here's a solid, okay. Here's a solid going to a liquid. Remember the kinetic energy, which is the average kinetic energy, temperature stays constant at a phase change. Here's pure liquid. Here's a liquid going to a gas. And then, of course, pure gas here. All right, well, if you're at a temperature change, you can't be at a phase change. So if I'm using the temperature change formula, it'll be MC change in T at a liquid phase because I have a change in temperature. Remember, this is kinetic energy or temperature. If I'm at the phase change where a solid is going to a liquid's going to a solid, there is no change in temperature. So I have to use mass times the heat of fusion. Fusion is melting. And this value of heat of fusion is given to you in Table B if you need it. Okay, and if I'm at the vaporization phase change, that would be mass times heat of vaporization. And that's also given in Table B. So clearly in the problem, I have a change in temperature. So I'm going to need the mass of my sample, its specific heat, which by the way is given in Table B as well as 4.18, and of course change in temperature is involved. Let's go back to the problem. So Q is equal MC change in T. So I've got 50 grams of water. Specific heat given in Table B is 4.18. Remember the heat of fusion that we talked about, heat of vaporization also in Table B. So 4.18. And the change in temperature, well, 20 degrees Celsius to 10. It's the difference. A change is the difference. So 20 minus 10 is 10. So let's just plug this in to our calculator. So you take your 50, straight plug-in question. 50 times 4.18 times 10, and you get 2090 joules. That's what we're solving for. Q is in joules. All right, so the closest and best answer is here. Now they put this in scientific notation, no trouble here. They just moved the decimal place. It was here, 1, 2, 3. So that's how they made it 2.09 times 10 to the 3. They move it 3 places to make it smaller. Okay, so just using scientific notation, clearly the answer is choice 2, and the answer for 45 is 2. 46. Okay, what occurs at one of the electrodes in both the electrolytic cell, that's the one that needs electricity, and the voltaic cell, that's the battery. You've got to know the difference here. The battery was first made by Alessandro Volta. An electrolytic cell is going to have electricity in its name to tell you that you need electricity. Any case, what occurs at both? Well, I will tell you that anox red cat occurs for both, which means oxidation occurs at the anode and reduction occurs at the cathode for both. Oxidation occurs as electrons are gained at the cathode. No. Red cat. Oxidation occurs as electrons are lost at the anode. Yes. We losing what? Electrons. Leo, right? Leo, the line says good. Losing electrons is oxidation. Oxidation occurs at the anode. 46 is choice 2. You have to know those mnemonics. You have to know that electrolytic cell and a voltaic cell, the battery, they both, electrons flowed from anode to cathode, and oxidation has to occur at the anode because if electrons are always flowing from anode to cathode, they have to come from the one who is losing to the one who is gaining. All right, number 47. Given the balance equation representing a reaction according to one acid-base theory, the H2O molecules do what? Well, look carefully. H2O in the future, this is the future side, okay, is doing what? Well, it has one more H and a positive. So this one has to be increasing in its H plus numbers. It's H2O with no charge. Now it's one extra H with a positive. Clearly, this one must have gained an H plus. So this one was giving off an H plus. And by the way, this is listed in a table. Okay, and in this table, what do we have? They give us acids, and look at the acid they gave us. They gave us HCl, and what the acids do? They give off H pluses. They have the H's in front. So clearly you could have known that the HCl was the acid because it had the H. But you know HCl gave off an H plus because in the future, what's left over after it donates the H is Cl. You can see that this thing must have lost. So this is acting as an acid because, well, it's listed under table K, or you can see that in its future, what's left over, called the conjugate base, is what's remaining after it donates. So clearly water must be gaining a proton, which is what bases do according to the one acid-base theory, which is the Bronston-Lowry theory, because I can see in the future, this is its conjugate acid as one more. So we would say that H2O is accepting H plus ions. Even if you didn't know anything about the theory, looking in the future of this reaction, you can see H2O has one more H plus in it. So 47 is clearly going to be 1. All right, number 48. When an atom of the unstable isotope sodium-24 decays, it becomes an atom of magnesium-24 because Na24 spontaneously releases what? Okay. Now, we are in the last couple of questions of your multiple choice, and of course, as we've talked about before, knowing where you are in the test is helpful, and we're in the nuclear area. So sodium-24, and let's make some room here to see what we're doing. All right, so sodium-24. Now, that number, Na24, is the mass number, so that's 24 above. I know its atomic number is 11 when I go to the periodic table. Okay, now it's becoming magnesium. All right, now magnesium is atomic number 12. And the 24 is its mass. So the question is, what particle, and I'm kind of giving it away, I guess, what particle, all right, is this? Okay, well, you should know that the numbers on top of one side of a nuclear equation have to equal the numbers, the top numbers on the other side. So 24 plus what is 24? Put that in your calculator, you'll get a 0. 12 plus what number equals 11? And you'd say -1. And what particle has a 0, -1? If you don't know already, you go to table O. Okay, let's go to table O. So which particle has a mass of 0 and a charge of -1? That's a beta particle. That's the one we're looking at. So of course it's a beta particle. 48 is 2. All right. 49. 49 states which balance equation represents nuclear fusion. Fusion means coming together with light nuclei. So if I look at number 4, you should realize that this is a big nucleus being split by a slow-moving neutron. This is nuclear fission. Just have to be able to identify. You're splitting the atom into smaller, more stabler atoms, and you're giving off more neutrons that could split more uraniums if you had something called a critical mass. Okay, but the fusion is this one, where you This is what's done in the stars, our star. This is where light nuclei of hydrogens usually come together to make our helium. Okay? Here is called natural transmutation, where we're giving off alpha particles. And here's another example of natural transmutation, where we're giving off beta particles. This is beta decay and alpha decay. But the nuclear fusion is choice 3, and you have to be able to recognize that light nuclei are fusing together to make the helium, and this gives off a lot more energy than a nuclear fission. And of course, doesn't have the nuclear waste the fission has. Some little other pockets of information may seem necessary to you. Okay, so 49 is 3. Number 50, last question on the PAT B1 here. Which reaction releases the greatest amount of energy per kilogram? I guess I just alluded to that if you were with me on question number 49, because we were identifying fusion. So any case, though they don't have fusion listed here, they do have fission again. Now, I want you to be very, very careful never to pick in the last 3 or 4 questions, whether it's number 28, 29, or 49, 50, those last questions, in the bottom of 1 through 30, it's the end of the course. Remember, they reset. They go through the entire unit 1 through 30. So number 29 and 30 are usually nuclear questions, and they go from 31 to 50 again. They go through the course again, and these are nuclear questions. Do not pick chemical reactions. These are about electrons being passed around. So these never give off the same amount of energy as the energy changes in a nucleus, because we're dealing with the strongest force in nature, believe it or not, called a strong force. So nuclear reactions always give off a lot more energy. So this is the bomb that were dropped in Hiroshima and Nagasaki. This is the fission bomb. Okay, and this is fission is a nuclear reaction, gives off a heck of a lot more energy because we're dealing and messing with the stabilities of the strong force. Here we're messing with the stabilities. So again, the nuclear equation is the answer. It's the only one here, so it makes it easy for you, but you should know nuclear reactions give off a heck of a lot more energy than regular chemical reactions. All right, and of course nuclear fission, the atomic bombs gave off tremendous amount of energy. So 50 is clearly going to be 1. And that concludes the multiple choice. All right, hope that helped. Now 1, 2, 3, 4, 5, 6, 7, 8. It says less than that. So this is my unsaturated hydrocarbon.